You already know what is enthalpy, but some few more thermodynamics properties are there. Actually, they are simply like enthalpy. What is it? Is it something new or something we can perceive? No, it is a mathematical relationship which has been found to be consistent, or it looks to be consistent. That is called enthalpy. So enthalpy, you know, internal energy we already know. So from now onward, we will be focusing very small segment, not completely, on chapter 5 in your textbook, which is talking about, our objective will be to talk about entropy. Entropy is also one of the thermodynamic property. It also, property means, what does it mean? Like internal energy, I told you, if I bring back to your original position, internal energy change will be 0. So some property relations are always there. Just a moment. Okay, sorry. So here we want to talk about a new thermodynamic property, that is entropy. But before we are talking about entropy, we also need to have a small discussion on second law of thermodynamics. First law, we already know that energy, whatever is coming into a system, either form of heat or that is going to be preserved. There is no loss, right? And if there is any change of heat transfer, it is going to transmit into internal energy. Energy is conserved. That concept is also there. Now, when we already know that there can be some difference between heat and work, the second law of thermodynamics is coming. It is mostly, second law of thermodynamics is mostly important for mechanical engineering and civil engineering people, because they will be talking on energy efficiency of thermal systems, particularly three engines varieties are there. Actually, we'll talk about that very small amount, about heat engine, heat pump, okay, and refrigeration. So three different form of energy transfer and work transfer process really happens in a thermodynamic system. Now, how does the things happens? How heat and work works together? Basically, if you have seen, some of you, if I ask you, I'll have many PPT today, but I'll try to keep in our discussion for this chapter here. Okay, I'll come back. From this slide, actually, I'll prefer to show here. So when I'm talking about second law of thermodynamics, how is it coming suddenly? That point is also important to know. So we already know from the very beginning of our class that if I am providing one system, if one system means I'm talking about, for example, some liquid or fluid, if something is there, and we are providing some heat to it, and possibly it is working like a piston. If I'm say like that, it is some gas is there, and this is a piston, and some fluid is there. I'm providing some heat to it, and it is going up, so it is giving some work. So heat to work, this process is known, and we have already seen that the heat and work are not same. If I provide some 10 joule of heat, it does not mean that I will get 10 joule of work. Is it possible? No, because some heat will be, please listen carefully, some of the heat will be stored in internal energy, right? So maybe work is done 8 joule and 2 joule of work is stored in internal energy because temperature is increased. Okay, so essentially, when our knowledge is there that heat is not necessarily equivalent to work, because there is some change in internal energy, that we already have appreciated, and we have solved some problems, but that was only one unidirectional systems. That means, for example, I'm providing heat means pump will go up, that's all. then there is no further work, right? So if you want to do further work, what you have to do? You have to press the pump back to its original position. Then only you can again heat it up and you can get some work. So essentially, what we have learned till now is a single process, not a cycle. Now, in case of all mechanical and civil engineering people who will be doing or who will be working on heat engine, heat pump, that is a continuous process, right? Like for example, in your refrigerator, okay, this is a inverse heat pump. How it works? How it keeps it cool? Because every time some heat is coming into a system, but still your foods are still stored at 4 degree or 7 degree, it is not increasing temperature, but environment is always hot, right? Environment is not cool, so every time it has to work against the temperature difference. And here you will have your compressor do the job. So some mechanical work is there, some work is there, and some heat transfer process is happening. Like steam engine, probably you know how the steam engine is supposed to work. So there is we are providing some heat first, right? In a crude sense, if I show you the steam engine diagram or steam engine, if you have seen, what is the crude sense? You're providing heat, then what happens? Creating steam, very good. Then steam will push up the piston up, some mechanical work is coming up, okay, then that's all? No, the steam should be cooled down again. So cooling is done, so steam will form liquid coming back to the original position. So this is a cyclic process. You are providing heat, you are getting work, you are losing some heat. This whole process when happens, then work and heat transfer, both things are happening. Okay, so you have to understand, when I'm having some work or heat transfer process, it is not always the same thing happening, that Q equal to W, not like that, but there will be some relationship. So let me tell you this diagram, what the diagram is saying. For example, I'm talking about, this is a steam engine, I'm showing in a schematic, it is not an engine picture, I'm not drawing. What is happening initially? You are providing some heat, okay, and if you're providing some heat, then you know steam is formed, some work is done, I'm getting some output, piston is pushing up. Now that is fine. Then what is there? If the piston is going one cycle, one half cycle, then you have to cool down the steam, other steam will be finished, right? That means you are taking out some heat then. Okay, you are taking out some heat out of the system. Because you are cooling the steam. And then once the cooling of the steam is done, you are also going to input some work. You have to put the piston back into the crankshaft. That means I am providing heat, I am getting some work, we are taking out some heat, I have to give some work, everything is there. So at least 4 component of heat transfer and work transfer is need to be done. Okay, it is cyclic process. Like here, if I want to put the piston up, it is fine, we are heating it up, so heat transfer work is done. Then what is the next thing? You have to cool it down, then only volume will come down, and you have to bring the piston back. So that means you are first doing some heat, then you are getting some work, then providing you some work and releasing some heat. This process happens most of the time, and that whole cube and whole of the work is maintained, but not this Q and this work, not like that. So for example, I'm putting some 100 joule and I'm getting some 80 joule of work, and here you are putting some 20 joule of 40 joule of work, and then how much I will get. So that concept is always valid. So whole Q and W will be always same, that is true, but this 100 does not mean that this will be 100, not like that. So overall heat and mass transfer into the process, this is going to give you the first law, which is talking about this, and second law is talking about that the heat and mass transfer process, the individual values of heat or mass, heat and work transfer is not essentially individually not same. I mean to say, this Q in, this Q out, work in, these whole processes are not same. They are all different. Only thing is that all the total cube, like this one and this one sum, all the work done, this one and this one sum, that is going to be 0. So overall heat and mass I'm sorry, always I'm killing is like a mass transfer, not necessarily work transfer. Heat and work transfer process are there. Now, when I'm talking about any heat engine, what is heat engine? Like steam engine is a heat engine. What is there? You have to give some heat. Of course, you will get back something, and in the meantime, you will get some work. So essentially, the diagram is I can show you here, like this case. Hey, you need not remember about all those things. I am not talking on them. I will talk only some limited portion here. Just a second, I'll put one slide. So we are talking about systems which are making heat transfer process, and it is always a cyclic process. Cyclic process you understood, right? Cyclic process of heat transfer and work transfer. Earlier we have done a linear process. We have already learned linear. Simple one step. You provide heat and you are getting some work. That's all we have learned till now. But now we are doing a cyclic process. So you are providing some heat, you are getting some work, you are putting some work inside, and you are releasing some heat. So 4 things. A cyclic process is happening. So essentially, we do not draw like that. We assume if this is a heat engine, then we say heat engine will get some heat from high temperature, of course, from high temperature source, because we are burning coal, for example. So high temperature heat is provided. So heat is being taken up by the system, and it is also releasing. What is the release? When you are condensing the steam, that release process is happening. You are also need to give some work to bring the piston back, and finally you are going to get some work. So this is work output, this is work input, this is heat input, this is heat output. So essentially, if I ask you to do some energy balance, how much you done work and how much you are getting, so actually the net work, how much work has been done, because you also need to give small amount of work. So work output minus work in, that is the net work out things you are getting from a engine. So you have to give some work, you are getting more work definitely. And for heat, it is also there. So how much of net work I am getting and how much of net heat consumed, that is, so I had Q in, I had Q out. So there is a net work and net heat transfer process. I calculated that. And when I will talk about any efficiency, so for example, I want to talk about the efficiency in this process. Efficiency of heat engine, that means how much net work I am getting and how much heat you are providing. You are actually providing Q in. Please try to understand. You are burning coal, okay? So your burning coal is your cost. It will automatically chill down, cool down, some heat will be lost to the environment, that is Q out. We do not bother. We only bother about how much of fuel is required. This is fuel. So net work by fuel in. Essentially, net work means W out minus WI and Q in. What is WO minus WI equal to Q in minus Q out? That you already understood. So this is the work, this is the heat. They will be same. So that is the first law of thermodynamics is telling all work is equivalent to all heat. So instead of W minus WI, I can also write Q in minus Q out divided by Q in. So what is happening? 1 minus Q out by Q in. Q out means how much heat is coming out of the system, heat loss, how much heat you are providing, how much of, so if I know these two things, what is the temperature you need to provide, what is the heat, not temperature, I'm sorry, heat is coming out of the system, I can find out the efficiency. And you see 1 minus something means, so efficiency will be always less than 1. So that is what we talked is about a heat engine diagram. Okay, it is a mechanical thermodynamics, you really need not understand. I'll very quickly, I will leave this, not much discussion here. Second law of thermodynamics was the point of discussion. That is only valid, it is particularly valid when work and heat interaction is happening in a cyclic process. Cyclic, you understand, right? I am heating something, steam is done, steam is cooled, and you bringing it back, piston is coming back, means point zero. So I am starting somewhere. We are doing one step, then you are going another step, then you are doing another step and coming back. So if the whole process of heat and work transfer is happened complete, that is known as cyclic process. And in this case, if the heat and energy is conserved, we will preferentially tell it as a Carnot cycle if the constant temperature process is happening. So what I mean that in this case, work transfer, heat transfer, all those processes are happening. This is one temperature, this is one temperature. So at a given temperature, some heat is transferred, then it is coming over here, then it is losing. For example, this is constant temperature T1, and this is another temperature, for example T out. So in this case, you are providing some heat. Here also you are losing some heat. In this case, you are going to come out from this temperature to this temperature process. It may be constant volume process. And in this case, you are releasing some work. Here, you have to give some work to get back. So for example, this is 0.1, this is 0.2, this is 0.3, and this is 0.4. This whole process they are doing in the same temperature, isothermal process, because Q1, this is temperature is T1, boiling coal temperature, burning coal temperature T1. This is, for example, environment, room temperature or atmospheric temperature 20 degree. So this is T2. So heat transfer is happening at a constant temperature process. So heat of this temperature of the surface is T1. This is the environment, outside environment, room temperature, atmospheric temperature T2, for example. This is T1, this is T2. Heat input is, for example, Q in. Heat losing out of the system is Q out. Some work is done during this process. Here work is needed during this process. Now this whole process when it is happening, this is known as Carnot cycle. Efficiency of heat engine process, I already told, it will be less than 1. And what is the efficiency we found? Efficiency equal to 1 minus Q out by Q in. Q out means how much heat is lost. Q in means how much heat is input. So if I'm providing, if any heat engine is there, you know that they are providing some 1000 joule of heat per second, and it is releasing some heat, some 80 joule per second, and then you can easily find out how much of efficiency. So 1 minus, for example, 80 by 100, for example. So I know this value, so 0.8, so efficiency is only 20%. So please try to understand, none of the engines we'll be talking in thermodynamic systems are perfect. So this was about heat engine, heat process, cyclic process, what I learned till now. So are you understanding what I'm talking about the thermodynamic systems? This is a mechanical components of your thermodynamics, and we will go back within a short period of time. Everything we need not discuss of the whole mechanical process, but some section I need to tell. So that was what I learned till now, or at least we try to learn, is that what is a cyclic process, right? I also told about heat engine. There are 3 terms I need to clarify. One is heat engine. What is that? Basically they are same type, only some difference is there. Heat engine means you have to provide some height at high temperature, you are providing some heat, and the system is also releasing some heat. Okay, so this is T1, this is T2. This is Q1 is the amount of heat, Q2 is the amount of heat lost, and there is some work input and there is some work output. Now you have to understand what is the purpose. The purpose of heat engine is to get work. Its purpose is to get work. Get work means I need to get this output should be always more than input. So I'm providing some just 2 joule and I am getting 100 joule. That means no problem. From 100 joule, some 2 joule I will simply give it back. Okay, so it is like if you want to do some business, you already know na, that you cannot have from zero investment, you cannot earn something. But for example, you are using some 2000, then you are making some 10,000 is possible. So these heat engines are like that. You have to have your initial investment here, heat transfer in this case is work. Then you will get some work out of the system. Heat engine purpose is to get work from heat transfer. Okay, and in this case, heat transfer, how is it happening? It is happening from high temperature to low temperature. So from high temperature, T1 is always high, T2 is low. That means you are boiling some water, and like in your case, room heating systems, right? You are providing heat, and heat is also being released. So in this case, temperature is higher, releasing temperature is low. That is called heat engine. This purpose is to get work. So here WO will be always greater than W input. Okay, and T1 will be always greater than T2. So Q1 will be also similarly Q1 heat transfer input will be always greater than heat output. But work output will be, remember here input is greater than output, but here output is greater than input. So work output is always bigger, that is heat engine. Now second terminology I will discuss, you please understand, that is heat pump. Heat pump is just opposite requirement. The requirement is totally, picture will be same only. Picture will be same. You need not worry on that. But in this case, what is the purpose of heat pump is to provide heat. You are having, for example, I want to, you have seen the refrigerators or you have seen the air conditioning, right? Air conditioning is going to make your system cooler than outside. But if I want to make it heating, room heating systems, like here in a cold place, then what is needed? They need to get heat from the environment. So for example, this is environment. Okay, from that I need to take heat. And I have to give it to inside room. Inside room is definitely more hotter than your outside. So here heat is taken from environment, it is given to inside the compartment. Purpose, what is the purpose of this one? So here also W input is there, W output is there, but what is the objective? To make heat transfer. Here not work is not important. Here only you want to have heat transfer from cold to hot. That means from low temperature to high temperature. That is not, it is actually opposite, right? It is not natural process. Heat normally transfer from high temperature to low temperature. That is normally, you know. So if I'm giving some rod, I'm keeping a rod at 100 degrees centigrade, okay, and room temperature is 30 degree. How the heat will transfer? From rod, heat will be transferred to room. From high to low happens. But if I ask you, no, I'm having a rod at 40 degree and room is 20 degree, and I want to maintain the rod 40 degree, what do you have to do? From room itself you have to provide it temperature and it will be cold. It is not possible. That means you have to give some work, you have to give some extra work. So in that case, what will happen? Your input of work will be definitely more than output. That means net you have to give work, or you have to work input. So to make the heat transfer happen, which is not really easy, it is just reverse process. So you must have more work done. So you will have a engine, mechanical engine, which is going to do the job transferring heat from low temperature to high temperature. So this is called heat pump. Okay, heat pump is clear. Now efficiency, all those things will be always same thing, no issue. As I already know that here Q1 and here Q2, Q1 will be definitely lower than Q2. What does it mean? Even if I'm taking 100 joule from surrounding air outside my room, actually I cannot transfer all 100. We'll be probably transferring some 80 joule or something like that. Okay, so even if I'm having some T2 and T, sorry, this value also I'm just correcting it. One thing you keep in mind, if it is T1, T2 is very low, and T1 is definitely higher. So T2 is lower than T1. We need to understand there is a relationship. We will be talking in our next class, that how much heat transferring from this process, how much is going into this process, how to know that. So as this is bigger than this, so it will be smaller than, so input, for example, this work done is 100 and work output is only 20, because you have to spend more work, then you will come back. So net you are inputting, if you are inputting means this input will be small. For example, here I am giving heat transfer is happening 30, but I will get it at 110 joule heat I will get at the high temperature. So that means total is same. You see, it has lost 80, work loss is 80, but heat gain is 80. Same thing. So overall Q plus W is all 0. But try to understand, from low temperature I am getting some 30 joule, it is providing some 110 joule, there is a work conversion. So most of the things is coming from the work. That is called heat pump. Heat engine we already told, this is heat pump. Okay, so this phenomena is going to make the things hotter. And the last part, which is all known, is about last part we will be talking about refrigeration. That is same picture we can draw, and just for definition I am telling, you need not really do any problem solving here. I'll take some another 5 minutes. Okay, now refrigeration, what happens in case of refrigeration? You need to understand the picture is just opposite. In this case, we are having a system like this. For example, in this case, what is refrigerator need to do? Refrigerator need to do is that from inside compartment, it has to continuously remove heat. Then only inside will be cold. So that means it is taking away some heat from low temperature. So for example, this is 4 degrees centigrade. I'm just telling. And here, for example, it is outside is 20 degree or 25 degree centigrade. So from 4 degree, it has to take out heat and it has to deliver to the atmosphere. So that's why you have seen outside of the refrigeration, it will be looks hot, because they are releasing the heat from inside, and it has to work, do some work. Picture is very similar to heat pump itself, but there is a objective is different. What is the objective here? So here objective is to releasing the heat. So for example, Q1 amount of heat is lost from refrigerator. This is cold refrigerator, and this is your ambient air. And Here it is taking Q1, it is giving Q2. Some work done is already there, W1. Compressor is doing this job, W2. Here also what will happen? In this case also same thing. Total heat transfer and total work transfer will be all balanced. But try to understand, when it is 4 degree, I am getting Q1, it is taking some heat from this and it is releasing heat more. So at Q2 is outside and it is releasing more. So for example, this is, I always understand, you have to understand that Q2 will be greater than Q1. That means how much it is taking away, it is releasing more. That means W1 should be greater than W2. You have to provide more work, then you will get from the cyclic process. So this is the diagram. In this case, what happens? Same formula will happen here. So if I say total W1 minus W2 is the work consumed, and here also same picture will happen. Q2 will be greater than Q1. That is always valid from first law of thermodynamics. Now, if I say its efficiency, refrigerator efficiency, efficiency means what is the objective? Okay, what is the objective here? Your objective was to transfer heat. What is the main objective? To provide heat Q2 to the environment? No, taking away heat from the refrigerator inside. So here objective is transferring heat from inside. Okay, and what is your input? How much of work is invested here? So for example, work investment, and you understand that when I am talking about Q1 and here work investment, that means this process I can write simply Q1, and work investment means W1 minus W2. So you got the point? So I can also write like this, Q2. So because why I could write like this, because Q2 minus Q1 is same as W1 minus W2. So instead of the work input, I can write like this. So Q2, so Q1, instead of Q1, I can write like this, Q2 minus Q2 plus Q1. I'm just writing Q2 minus Q1. So instead of the numerator, I'm just writing plus Q2 minus Q2. So no change actually. So I can write like this. So this is becoming Q2 divided by Q2 minus Q1. And this part, if you see, is equal to minus 1. Okay. So depending on that, its values as how much Q1 is there, how much Q2 minus Q, only numerical values. So efficiency can be very low. How much of work transfer and heat transfer is taking place, depending on these values of efficiency of refrigeration, we can calculate. So that was a discussion till this point about heat engine, heat pump, all those things. One last property I will talk, and then we'll close all those assertions. We are not going to ask any numerical from that. That is not needed. The last property, there is a one thermodynamic property I need to tell. What is seen here in most of the process of heat engine and heat pump, as I telling, there is a temperature in the receiving side. When I am burning coal, some temperature is definitely there. Constantly we are maintaining. Temperature is constant. We are only providing more coal. So that means more heat. So definitely there is a temperature here, and there is one heat transferring process in that surface. Similarly, at the receiving edge also same thing happens. It is schematic diagram only, nothing more. Here also some T2 is the temperature, and for example here Q2 is the amount of heat lost. So here heat input, here it is output. Okay, this is one surface, exchange surface. Because this heat transfer is happening, one formulation is always there, Q1 by T1 equal to Q2 by T2. This observation comes from depending on how much temperature is there, how much temperature of the outside junction, how much temperature of the inside junction, they will be all proportional relation with temperature. So if the T1 is high, and then it will be Q1 will be always high. If T2 is high, then Q2 will be always high, because heat transfer depends always on temperature difference. So Q is somehow related to temperature gap. Okay, how much heat is transferred, and that is means delta. So essentially, it is something Q1 minus Q2 is nearly proportional with T1 minus T2, and that's why these assumptions look sense, not always true. That Q1 by T1, it depends on how much heat and transfer is taking place, Q2 by T2. So essentially, in all thermodynamic process of cyclic process, Q by T is going to be constant. Anytime Q by T is going to be constant. And heat transfer is always dependent on temperature. Now, if this is happening, for example, not in a constant temperature or maybe over a temperature range, then in a cyclic process, we can also do dq by T. Whole temperature change over the process in a cyclic process, if we can going to calculate, if it is reversible, we can say it is zero. Whole transfer here Q by T and here also Q by T is same. Of course, negative sign will be there, resulting in zero. So in a whole cyclic process, Q by T relationship is going to make no change, and that conception is going to evolve in a new way that is known as entropy of a system. Entropy tells you how much heat is going to be transferred to the system and how at what temperature. So this relationship, because it is appearing to be a constant terms, we refer these changes as, so if it is happening at constant temperature process, then change of entropy is a thermodynamic term, thermodynamic property. We are only telling, there is no such any physical meaning of entropy. Entropy is change of or heat transfer process depending on the temperature interface we are talking about. So entropy is dq by T, how much heat is transferred and at what temperature we are doing. And this will be used for calculation of the other thermodynamic parameters as well. So entropy essentially tells the heat transfer against a temperature gradient. Essentially, how much heat it can transfer and at what temperature. Entropy is more of a system. Entropy means, in some physicists normally speak entropy as the chaos. We do not see like that. It is only told by Fixer's terminology. In case of our sense, in our thermodynamics principle, entropy is how much of heat it is going to take inside the system or losing out of the system, and how at what convenient temperature. Why this is important? It can take more heat without changing its temperature, means molecular motions is increased. So temperature is constant, but I'm providing heat. If temperature constant means internal energy is not doing anything, right? Internal energy is not changing. So I'm providing some heat to a system, heat transfer is there, temperature is not changing, then what is happening? Then these energy are all about molecular motions, not kinetic energy. It is not macroscopic unit. Internal energy is going to give the temperature rise. If they're colliding, then it is increasing temperature, internal energy. But I'm providing some heat, they are only making chaos without any collision, perspective is not considered. So that means it is becoming more chaotic, and chaotic and entropy are synonymous from this term. So essentially, heat transfer to a system, how much temperature change, that logs entropy. And then what is our use for that? Entropy, you need to understand in many process we can actually calculate the entropy change. For example, I am having some ice in a at minus 10 degree, for example, and it is, what will happen if I keep some ice at minus 10 degree in a plate and keep it in room temperature? What will happen? Slowly, the ice will melt, yes, and room temperature is, for example, 25 degree. So what is the steps it will happen? So minus 10 degree, the ice will go to 0 degree first. It will be still ice. It will reach 0 degree centigrade. Then it will become 0 degree water. Still 0 degree. It will become water. Then again it will take heat from ambient atmosphere, right? It will take heat from atmosphere, and finally the water will become 25 degree. If you keep it long time, then you will see these 4 steps will happen. So what does it mean? This is a thermodynamic. It is not a cycle. Of course it is not a cycle. If it is not a cycle, means entropy change will be there. Is it cycle? Because we started at minus 10 degree ice. Have we come back to minus 10 degree? No, we are at 25 degree water, but it is happening in a sequential steps or process. So when I'm starting with minus 10 degree centigrade temperature ice, and if the outside temperature is 25 degree, then what is essentially happening? Our atmosphere, our air is losing heat, and that heat is taken care, it is utilized for minus 10 degree ice to become 0 degree ice, 0 degree ice to become 0 degree water, 0 degree water to become 25 degree water. So there is heat transfer during this process. So some Q1, Q2, and some amount of heat transfer is happening, Q1, Q2, Q3. Each of the step there will be some entropy change, some delta S. S is referred as entropy. So here also something is happening during this process, something is happening during this process, something is happening during this process. So overall change of entropy we can calculate, and I think we'll be finishing another 2 minutes, not much. So if I ask you to calculate entropy in this kind of systems, I'll take another 2 slides. Okay. Now how to calculate? I only know the theory. I have not done the calculation. So first case, what is happening? Minus 10 degree centigrade ice is becoming 0 degree centigrade ice. I told you entropy change ds equal to dq by t. Now dq means heat transfer. Like a metal or anything else, if the temperature is increasing, that means there is heat transfer is happening, and it always depends on specific heat, right? If it is a metal, then how much heat transfer? H, na, Q or H equal to m into specific heat into temperature change, that right? Or any 10 degree to 20 degree, if I'm hitting something, so I know the mass, I know the specific heat, I know the temperature change. So dq is also same thing as mass. I know, for example, 1 kilogram mass. Specific heat, for example, ice, specific heat for ice, and dt, mass is, for example, 1 kilo. So during the whole process, how much heat is transferred? Integrate. So during this process, minus 10 degree to 0 degree ice, C is specific heat of ice, something is given. Okay, and remaining is integration of dt by t. Integration of dt by t means ln t. So C of ice, specific heat of ice, ln T2 by T1. T2 means final temperature. What is 0 degree? Starting minus 10 degree. So you can do that. C ice ln. Of course, temperature is all in Kelvin scale. So 0 degree, for example, 273, and here 263. You can calculate. So this is becoming delta S. If I integrate the whole process in between the small step from ice to this one, you can do that. Okay, fine. Specific heat I did not tell you. You can have some values. Now 0 degree ice to 0 degree water. Again, second step. So second step, entropy change I will calculate. That is again dq by t. But here also temperature 0, here also temperature 0. Temperature is not changing. Okay, that means temperature is constant. So essentially then only it depends on dq, how much heat is required. So it depends on latent heat, right? You know, latent heat is the heat required for phase transfer from liquid solid to liquid at same temperature. So latent heat, for example, if I know for ice, I'll put it latent heat values. For example, 242 kilocalorie per joule, per kg. I can put these values dq. This is known, and temperature is 0 degree, so 273. So here only heat transfer by temperature. No integration is required because this is at same temperature, no change in temperature is happening. Okay, so this is always 273 is constant. Now it is water, I am heating, again this formula will come. That means in the whole process the total change in entropy is just change in entropy for first case, change of entropy in second case, change of entropy in third case. If I do the calculation, for example, I'm getting I'm telling I'm getting some 100. Okay, what is the unit for entropy? dq by t. That means joule per Kelvin. For example, I'm getting like this. So your system, your container containing the ice, water, all those things, entropy is increasing. For example, it may decrease, just simply talking. And what happens in this case when it is changing the entropy of the system? Who is losing heat? Your atmosphere, right? Atmosphere is providing you heat. It is losing some heat. So change in atmosphere will also be there. Change of entropy in atmosphere or surrounding. Of course, do you think if some ice is melt, the room temperature will come down? Definitely not, but we can still calculate. So next day I will discuss very small thing about entropy overall system, and we will come to the thermodynamical property or property of pure fluids in our next class. This very quick description of entropy, quick assessment how to calculate, how the heat engine, heat pump, all those things are coming, and concept of entropy, how it is coming, why it is coming, q by t remains constant in a cyclic process. So to know that, we started the introduction of entropy. Okay, I think some of things you understood, not everything. Okay, if you have any queries, you could have told me, otherwise I'll stop this class. Okay, so you can leave this class now. It is 11:50. If you have nothing to discuss.
Thank you, sir.
Thank you. Thank you
Thank
all.
you, sir. Thank you,
Thank
sir.
you.
Thank you, sir.